Why and how can a nucleus decay? Does radioactive decay produce anything? These are the main questions we will try to answer during this lecture. Briefly speaking, radioactive decay is a natural process in which an unstable atomic nucleus modifies its internal configuration or transforms into another nucleus to reduce the overall energy content. To describe the main features of the process, we must remind the famous Einstein formula, E equals mc squared. This equation highlights that energy and mass are equivalent. They are two different ways of looking at the same physical property. Therefore, mass can be converted into energy and vice versa. Unstable nuclei exploit this conversion process to change their conditions and move towards more stable configurations. Let us go into the details of the actual processes that nuclei use to feel better. To do so, we can make use of the so-called table of nuclides. This table collects all known nuclei, organized by the number of neutrons n on the x-axis and by number of protons z on the y-axis. Black regions refer to stable isotopes, while the different colors represent the different decay modes of unstable isotopes. Let's start from the regions highlighted in yellow. All refer to heavy nuclei. These radioactive nuclei can spontaneously decay by emitting a nucleus of helium-4, which consists of 2 protons and 2 neutrons. This particle was called alpha by Rutherford, who studied its properties of charge and mass by examining the emissions of radium. When a nucleus decays by emitting an alpha particle, it transforms into another nucleus. Its mass number A decreases by 4 and the atomic number Z by 2. For example, uranium-238 decays to thorium-234 by emitting an alpha particle. To understand the effects of the process, we can write an energy balance. Initially, we have only the nucleus of uranium-238 at rest. So, the unique energy input is the one associated to its mass. After the decay, we have the thorium-234 nucleus and the alpha particle, both with their masses and their acquired kinetic energies. By rearranging the terms of the equation, we can highlight where the energy comes from and where the energy goes. Both members define the so-called Q value of the process, a quantity that represents the amount of energy available for the transformation. A positive Q value means that the process can occur spontaneously. Given the great difference between masses of the two decay products, the energy provided by the process is taken almost entirely by the alpha particle. Moreover, due to conservation laws, alpha particles are emitted at a specific energy value. In other words, they are monoenergetic. Alpha decay consists in the release of a small pack of nucleons from a heavy nucleus. There is another option that nature gives to lighter nuclei, a decay mode which consists in the conversion of a nucleon from one type to another. This is the so-called beta decay, a name that actually refers to 3 different processes: beta minus, beta plus, and electron capture. Let's have a look at their main features. Let's go back to the table of nuclides. The second decay mode we are going to analyze refers to the light blue regions, the so-called beta minus decay, which involves the conversion of a neutron in a proton. The mass number A of the nucleus remains unchanged, while its atomic number Z increases by 1. Carbon-14, for example, decays into nitrogen-14. This conversion process involves a variation of the charge of the nucleus. Therefore, to obey the law of charge conservation, the transformation proceeds with the emission of 1 electron. But pay attention, the emitted electron does not belong to the ones that orbit the nucleus, but is a brand new particle created in the nucleon conversion process. And that's not all. The creation of a particle, the electron, is let's say, compensated by the creation of an antiparticle, called antineutrino. The Q value of the process results to be the difference between the atomic masses of the parent and daughter nuclei. This energy is essentially shared by the two light particles, the electron and the antineutrino. The different possible combinations of this sharing lead to an important experimental evidence. The kinetic energy of electrons emitted in beta- decay is continuously distributed from 0 up to the Q value. Going back to the table of nuclides, the pink regions represent the beta plus decay, in which a proton inside the nucleus spontaneously transforms into a neutron. Thus, a nucleus that decays beta plus decreases its atomic number Z by 1, maintaining its mass number A unchanged. For example, fluorine 18 decays into oxygen 18. The charge variation is compensated by the creation of a positively charged electron, a sort of anti-electron called positron. Also, the creation of an antiparticle comes with the creation of a particle called neutrino. As in the case of beta- decay, positrons are emitted with energy values continuously distributed from 0 up to the Q value. By looking at the Q value calculation for beta plus decay, we can observe its energy constraint. 1022 keV of the energy gained from the change in the atomic mass are lost in triggering the process. That is probably why nature adopts another type of process, the so-called electron capture. In this third beta transition, a proton switches into a neutron by capturing an atomic electron. Being the electron already present in the system, the Q value is again equal to the change in the atomic mass. And do not forget the final product of the electron capture, a neutrino, generated to compensate the disappearance of the electron. In many alpha and beta decay processes, the daughter nucleus is left in an excited state. Then, the nucleus can rapidly de-excite by emitting electromagnetic radiation called gamma rays. This process is called a gamma decay. It does not involve a transformation of the nucleus, but rather a decrease of its energy content. The emitted gamma ray carries the excitation energy of the nucleus and therefore it is monoenergetic. For example, cesium-137 transforms to a beta- decay into an excited state of barium-137. Then, barium-137 de-excites and reaches its ground state by emitting a gamma ray. To conclude, during this lecture we have seen how nature provides many different decay modes to nuclei to reach the best possible energy condition. All modes are spontaneous and therefore natural, thanks to the release of energy associated to the reduction of masses, a clear experimental evidence of the validity and the importance of Einstein's famous law E = mc².